Hello, today's topic of discussion is hypergeometric function. In this chapter, we have two modules. We will start with the basic definition of the hypergeometric function. We will show that the solution of the hypergeometric equation is the hypergeometric series. We will also show the integral representation followed by Gauss theorem, Vandermonde's theorem and Kummer's theorem. The term hypergeometric function was introduced by John Wallis in his book in 1655, which also appear in the work of Euler, Gauss, Riemann and Kummer. Barnes and Mellin studied their integral representations and their special properties were studied by Schwarz and Gauss. However, the first in-depth treatment was executed by Gauss in 1813, where he presented most of the properties of hypergeometric functions what we see today. Hypergeometric function has motivated the development of several domains such as complex functions, Riemann surfaces, differential equations and so forth. Here we will concentrate on hypergeometric function of one variable only. Before starting the hypergeometric function, let us define Pochhammer's symbol. Pochhammer's symbol is defined as alpha suffix n, which means alpha into alpha plus 1 into alpha plus 2 dot dot alpha plus n minus 1, where alpha 0 is equal to 1, n being a positive integer. We can simplify this by multiplying both numerator and denominator by 1, 2, 3 dot dot alpha minus 1, and if you do that, we will get 1, 2, 3 dot dot alpha minus 1 alpha, alpha plus 1 alpha 2 plus 2 dot 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 alpha plus n minus 1, which is alpha plus n minus 1 factorial, and this can be expressed as gamma function alpha plus n divided by gamma alpha. Hypergeometric function is defined as f alpha beta gamma x, which is equal to summation r equal to 0 to infinity alpha r beta r gamma r x to the power r by r factorial. And if we expand this, we will be getting this is equal to 1 plus alpha into beta by gamma into x by 1 factorial plus alpha into alpha plus 1 beta into beta plus 1 divided by gamma into gamma plus 1 into x square by 2 factorial plus dot dot dot. If alpha equal to 1 and beta equal to gamma, then the hypergeometric series reduces to the standard geometric series 1 plus x square plus dot dot dot. We now look into the hypergeometric equation and its solution. The hypergeometric equation is given by x into 1 minus x d2y dx square plus gamma minus alpha plus beta plus 1 into x into dy dx minus alpha beta y equal to 0. This equation was studied in detail by Gauss in connection with his theory of the hypergeometric series, but actually it was Euler who had worked with this equation and its solution at an earlier date. Using Frobenius method, we now solve this hypergeometric equation given by equation 3, where gamma is not an integer. We rewrite the equation in the form d2y dx square plus px dy dx plus qx equal to 0, where px is equal to gamma minus alpha plus beta plus 1 into x divided by x into 1 minus x, and qx is equal to minus alpha beta divided by x into 1 minus x. We observe that both x px and x square qx are both analytic at x equal to 0, which implies that x equal to 0 is a regular singular point of equation 4. We assume the series solution of 4 to be of the form y equal to summation m equal to 0 to infinity C m x to the power k plus m, where C0 not equal to 0, given by equation 5. This implies dy dx is equal to summation m equal to 0 to infinity C m k plus m x to the power k plus m minus 1 and d2y dx square equal to summation m equal to 0 to infinity C m k plus m minus 1 x to the power k plus m minus 2, given by equation 6. We substitute the values of y dy dx d2y dx square in equation 2 and we obtain after simplification summation m equal to 0 to infinity C m k plus m minus 1 plus gamma k plus m x to the power k plus m minus 1 minus summation m equal to 0 to infinity C m k plus m into k plus m plus 1 plus alpha plus beta plus 1 k plus m plus alpha beta into x to the power k plus m equal to 0, given by equation 8. Which after simplification give equation 9 and equation 10, given by summation m equal to 0 to infinity C m k plus m minus 1 plus gamma x to the power k plus m minus 1 minus summation m equal to 0 to infinity C m k plus m plus alpha k plus m plus beta x to the power k plus m equal to 0. We now equate to 0 the coefficient of smallest power of x, in this case x to the power k minus 1, to get the initial equation as k into k minus 1 plus gamma equal to 0, because C0 is not equal to 0, and this implies the values of k are 0 and 1 minus gamma. To obtain the recurrence relation, we equate to 0 the coefficient of x to the power k plus m minus 1, and we will get Cm into k plus m minus 1 minus gamma minus Cm minus 1 k plus m minus 1 plus alpha k plus m minus 1 plus beta equal to 0. Rearranging the terms, we will get equation 12, which is Cm is equal to k plus m minus 1 plus alpha k plus m minus 1 plus beta divided by k plus m minus 1 minus gamma. Substituting k equal to 0 and m equal to 1, 2, 3 dot 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 successively in equation 12, which is renamed here as 13, we will get C1 is equal to alpha beta divided by 1 dot gamma into C0, C2 equal to alpha plus 1 beta plus 1 divided by 2 times gamma plus 1 into C1, where you substitute the value of C1 from the first expression and you will be getting alpha into alpha plus 1 beta into beta plus 1 divided by 1 dot 2 gamma into gamma plus 1 C0. In the similar manner, we can find C3 is equal to alpha into alpha plus 1 into alpha plus 2 beta into beta plus 1 into beta plus 2 divided by 1 dot 2 dot 3 gamma into gamma plus 1 into gamma plus 2 C0. We substitute all the calculated values of Ci's in y equal to summation m equal to 0 to infinity Cm x to the power k plus m with k equal to 0, and we replace C0 by some constant capital A, and we get our solution as y equal to A into 1 plus alpha beta divided by 1 dot gamma x plus alpha into alpha plus 1 beta into beta plus 1 divided by 1 dot 2 gamma into gamma plus 1 into x square plus alpha into alpha plus 1 into alpha plus 2 beta into beta plus 1 into beta plus 2 divided by 1 dot 2 dot 3 gamma into gamma plus 1 into gamma plus 2 x cube plus dot dot dot. Putting a equal to 1, the series which we will get is called the hypergeometric series and is represented by the function f alpha beta gamma x. We next put k equal to 1 minus gamma and then 12 reduces to Cm is equal to alpha dash plus m minus 1 beta dash plus m minus 1 divided by m into gamma dash plus m minus 1 into Cm minus 1 given by equation 15, where alpha dash is equal to 1 minus gamma plus alpha, beta dash is equal to 1 minus gamma plus beta, and gamma dash is equal to 2 minus gamma. We substitute m equal to 1, 2, 3 dot 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 successively in equation 15, and we will get C1 is equal to alpha dash beta dash divided by 1 dot gamma dash into C0, C2 is equal to alpha dash plus 1 beta dash plus 1 divided by 2 times gamma dash plus 1 into C1, where you substitute the value of C1 from the previous expression to get alpha dash into alpha dash plus 1 beta dash into beta dash plus 1 divided by 1 dot 2 dot gamma dash into gamma dash plus 1 into C0. Substituting all the values of Cj's with k equal to 1 minus gamma and replacing C0 by the constant b, we will get y equal to b into x to the power 1 minus gamma 1 plus alpha dash beta dash divided by 1 dot gamma dash x plus alpha dash into alpha dash plus 1 beta dash into beta dash plus 1 divided by 1 dot 2 gamma dash into gamma dash plus 1 x square plus dot dot dot. If we put b equal to 1, the series which we will be getting is denoted by x to the power gamma minus 1 f of alpha dash beta dash gamma dash x, that is x to the power gamma minus 1 f of 1 minus gamma plus alpha, 1 minus gamma plus beta, 2 minus gamma and x, which is another independent solution of this hypergeometric equation. Therefore, we conclude that the general series solution of the hypergeometric equation given by equation number 2 can be written in the form y equal to a times f alpha beta gamma x plus b times x to the power gamma minus 1 f of 1 minus gamma plus alpha, 1 minus gamma plus beta, 2 minus gamma x, where a and b are arbitrary constants. We have just learned about the solution of the hypergeometric equation, which is the hypergeometric series. We will now look into the differentiation of the hypergeometric function, integral representation of the hypergeometric function, followed by Gauss theorem, Vandermonde's theorem, and Kummer's theorem. We will now show that the hypergeometric function can be directly differentiated, and we have to prove that ddx of f alpha beta gamma x is equal to alpha beta by gamma f of alpha plus 1 beta plus 1 gamma plus 1 into x. We use the definition of hypergeometric function and we get f of alpha beta gamma x is equal to summation r equal to 0 to infinity alpha r beta r divided by gamma r into r factorial into x to the power r. We differentiate both sides with respect to x and we get ddx of f is equal to summation r equal to 0 to infinity alpha r beta r divided by gamma r into r factorial r x to the power r minus 1, which is equal to summation r equal to 1 to infinity alpha r beta r divided by gamma r into r minus 1 factorial x to the power r minus 1. Please note, we have replaced this summation from r equal to 0 to r equal to 1 because here it is r minus 1 factorial and you cannot put r equal to 0 here, which will be undefined. We next replace r minus 1 equal to m, and we will get ddx of f is equal to summation m equal to 0 to infinity alpha m plus 1 beta m plus 1 divided by gamma m plus 1 into m factorial x to the power m, which is equal to summation m equal to 0 to infinity alpha into alpha plus 1 m beta into beta plus 1 m divided by gamma into gamma plus 1 m into m factorial x to the power m. We take alpha, beta, gamma outside the summation notation, and we will get ddx of f alpha, beta, gamma x is equal to alpha, beta by gamma summation m equal to 0 to infinity alpha plus 1 m beta plus 1 m divided by gamma plus 1 m into m factorial x to the power m. Please note alpha plus 1 in the suffix m is the Pochhammer symbol which we have already defined before, and therefore we conclude ddx of f alpha beta gamma x is equal to alpha beta by gamma f of alpha plus 1 beta plus 1 gamma plus 1 x, which is our required result. We next look into the integral representation for the hypergeometric function. We have to show that f alpha beta gamma x is equal to 1 by beta function beta comma gamma minus beta integration 0 to 1 t to the power beta minus 1 1 minus t whole to the power gamma minus beta minus 1 1 minus xt to the power minus alpha dt with gamma greater than beta greater than 0. We use the definition of hypergeometric function involving Pochhammer's symbol, and we get f alpha beta gamma x is equal to summation n equal to 0 to infinity alpha n beta n gamma n x to the power n by n factorial, which is equal to summation n equal to 0 to infinity alpha n beta gamma function beta plus n divided by gamma function beta gamma function gamma divided by gamma function gamma plus n x to the power n by n factorial. This again we have introduced before in the Pochhammer symbol slide, which after simplification gives gamma divided by gamma beta gamma function gamma minus beta summation n equal to 1 to infinity alpha n beta plus 1 gamma function gamma minus beta divided by gamma function beta plus n plus gamma minus beta into x to the power n by n factorial, given by equation 20. This can be simplified as gamma function gamma divided by gamma function beta gamma function gamma minus beta summation n equal to 1 to infinity gamma function n beta function beta plus n gamma plus beta x to the power n by n factorial, where gamma is greater than beta and which is positive, given by equation 21. And this can be written as, using the definition for beta function, gamma function gamma divided by gamma function beta gamma function gamma minus beta integration 0 to 1 t to the power beta minus 1 1 minus p to the power gamma minus beta minus 1 summation n equal to 0 to infinity alpha n x t to the power n divided by n factorial dt, given by equation number 22. And hence this can be written as gamma function gamma divided by gamma function beta gamma function gamma minus beta integration 0 to 1 t to the power beta minus 1 1 minus t to the power gamma minus beta minus 1 1 minus xt whole to the power minus alpha dt, given by equation 23. This is one of the integral representation for the hypergeometric function, which is given by equation 23. You can simplify it further by replacing this particular expression by 1 by beta function beta into gamma minus beta integration 0 to 1 t to the power beta minus 1 into 1 minus t to the power gamma minus beta minus 1 minus x t to the power minus alpha dt, given by equation 24. And hence, we can take both equation 23 and equation 24 as our integral representation for the hypergeometric function. We now state Gauss theorem in connection with the hypergeometric function. Let f alpha beta gamma x be the hypergeometric function, then we have to prove f of alpha beta gamma 1 is equal to gamma function gamma minus beta minus alpha divided by gamma function gamma minus alpha gamma function gamma minus beta. Now, from the integral representation of the hypergeometric function, which is given in equation 23, we substitute x equal to 1 and we will get f of alpha beta gamma 1 is equal to gamma function gamma divided by gamma function beta gamma function gamma minus beta integration 0 to 1 t to the power beta minus 1 minus t to the power gamma minus beta minus 1 minus t whole to the power minus alpha dt. We simplify these two expressions and we will get gamma function gamma divided by gamma function beta into gamma function gamma minus beta integration 0 to 1 t to the power beta minus 1 minus t whole to the power gamma minus beta minus alpha minus 1 dt. And if we use the formula 0 to 1 t to the power p minus 1 minus t to the power q minus 1 dt is equal to the beta function pq, which is equal to gamma function p gamma function q divided by gamma function p plus q, we will get gamma function gamma divided by gamma function beta into gamma function gamma minus beta multiplied by gamma function beta gamma function gamma minus beta minus alpha divided by gamma function beta plus gamma minus beta minus alpha, which after simplification gives f of alpha beta gamma 1 is equal to gamma function gamma minus beta minus alpha divided by gamma function gamma minus alpha gamma function gamma minus beta, which is our required result. Next, we prove Vandermonde's theorem in connection with hypergeometric function. Here we have to show that if f alpha beta gamma x be the hypergeometric function, then f of minus n beta gamma 1 is equal to gamma minus beta suffix n divided by gamma n, which is the Pochhammer symbol. Now, from Gauss theorem, we have with alpha equal to minus m, we will get f of minus n beta gamma 1 is equal to gamma function gamma minus beta plus n divided by gamma function gamma plus n gamma function gamma minus beta. So, what we do is we substitute alpha equal to minus n here in this expression. Which after simplification will give gamma function gamma minus beta plus n minus 1 into gamma minus beta plus n minus 2 gamma minus beta into gamma function gamma minus beta divided by gamma plus 1 minus 1 gamma plus n minus 2 dot 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 gamma, gamma function gamma and gamma function gamma minus beta, and which can be simplified, and using the Pochhammer symbol we will get gamma minus beta suffix n divided by gamma suffix n. Hence, we prove the Vandermonde's theorem, which is f of minus n beta gamma 1 is equal to gamma minus beta suffix n divided by gamma suffix n. In our last theorem, which is the Kummer's theorem, we have to show that if f alpha beta gamma x be the hypergeometric function, then f of alpha beta beta minus alpha plus 1 minus 1 is equal to gamma function beta minus alpha plus 1 gamma function beta by 2 plus 1 divided by gamma function beta plus 1 gamma function beta by 2 minus alpha plus 1. So, basically we have to replace this x by minus 1 and this gamma by beta minus alpha plus 1. Here we use the integral representation of the hypergeometric function with x equal to minus 1 and gamma equal to beta minus alpha plus 1, and we will get the required expression is equal to gamma function beta minus alpha plus 1 divided by gamma function alpha, gamma function beta minus alpha plus 1 minus beta integration 0 to 1 t to the power beta minus 1 1 minus t to the power beta minus alpha plus 1 minus beta minus 1 1 minus t to the power minus alpha dt, which after simplification gives gamma function beta minus alpha plus 1 divided by gamma function beta into gamma function 1 minus alpha integration 0 to 1 t to the power beta minus 1 1 minus t to the power minus alpha dt, which can be simplified as gamma function beta minus alpha plus 1 divided by gamma function beta gamma function 1 minus alpha integration 0 to 1 t to the power beta minus 1 1 minus t whole to the power minus 2 alpha dt. We put t square equal to u, so that dt is equal to du by 2 square root of u, and hence we will get the previous expression is equal to gamma function beta minus alpha plus 1 divided by gamma function beta gamma function 1 minus alpha integration 0 to 1 u to the power half whole to the power beta minus 1 1 minus u whole to the power minus alpha du divided by 2 square root of u, which after simplification gives gamma function beta minus alpha plus 1 divided by 2 times gamma function beta gamma function 1 minus alpha integration 0 to 1 u to the power beta by 2 minus 1 1 minus u whole to the power 1 minus alpha minus 1 du, and hence using the formula integration 0 to 1 u to the power p minus 1 1 minus u to the power q minus 1 du is equal to beta function pq, which is equal to gamma function p gamma function q divided by gamma function p plus q, we will get the simplified expression as gamma function beta minus alpha plus 1 divided by 2 times gamma function beta into gamma function 1 minus alpha multiplied by gamma function beta by 2 gamma function 1 minus alpha divided by gamma function beta by 2 plus 1 minus alpha. And hence multiplied both the numerator and denominator by beta, we get our required result as f of alpha beta beta minus alpha plus 1 minus 1 is equal to gamma function beta minus alpha plus 1 gamma function beta by 2 plus 1 divided by gamma function beta plus 1 gamma function beta by 2 minus alpha plus 1, which is our required result. So, in this module we have learned about the solution of the hypergeometric series, which is the solution of the hypergeometric equation, which is followed by the differentiation of the hypergeometric function, the integral representation of the hypergeometric function, Gauss theorem, Vandermonde's theorem and Kummer's theorem. In our next module 2, we will look into the confluent hypergeometric series. Thank you.